number one, it's an example of the emphasis we're trying to place this year on the relationship between hardware and open source software. And also, it's something for those of you who had to give up going to Android TO because it conflicted with our event this week. It gives you some exposure to Android stuff. So I'd like to present some professors who have been teaching for years and years in our electronics and computer engineering and technology-based programs, Chris Rodgers and Wayne Bryan.
Thanks very much, Evan. So Wayne and I have been working with students on a number of different fronts. I'm particularly involved in student projects, their final technology projects at Seneca College. Wayne's one of our lead professors in programming technology, does a lot of work in the field as well. So we wanted to work together on this to try to bring these two worlds together, and that's what we're going to be talking about today. Basically, we're going to give a bit of an overview of where this came from. Wayne's going to talk a bit about some of the key things about working with Android. He's going to give you a simple example of programming an output with Android, and then take into consideration some other programming things you want to be concerned about, for instance, with programming with multi-threading. And then I'm going to talk about some basic principles about doing hardware interfacing. I think there's a lot of software people here, and I wanted to show you some of the basic principles that if you follow these guidelines, you'll be good to go for interfacing your Android devices with any number of things. And all throughout this presentation, we'll be doing some demonstrations. So how this all started was in the TPJ 655 project, our final technology project that takes place throughout the year, but I managed the one in the wintertime. Two of our students, Rolando Singh and Andrew Ng, wanted to do some programming in Android, and they wanted to interface that with the real world. Wayne and I have been talking about building an elevator model, which we have here and we'll demonstrate a little later, for some time now as a way of actually getting programming students to do hardware. Because sometimes I think there's a disconnect between the two, and it doesn't have to be, and that's really what we want to talk about today. And we're very fortunate to have Martin Peros, who's a retired instructor from our school, actually came back and built this elevator out of bits and pieces in his home shop, and these kind of rails you can get at Home Depot, in fact. So without his expertise, this particular device wouldn't have happened. And here's to Andrew and Rolando during their presentation last April. I'm very happy. So thanks to them for sharing their work with us. Their device was built using a Bluetooth dongle and also operates with a Samsung tablet, although today Wayne's going to be actually demonstrating it not only with a Samsung tablet, but with an HTC cell phone. So a system overview as designed by Andrew and Rolando based on a Samsung tablet was connected to what's called a IOI or a yo-yo board, which is all the rage under SparkFun. We'll give you references to that a little bit later. They're connected together using Bluetooth, and then there's a bit of interfacing that goes on. We'll look at that in a minute. Logic I/O, there's an enormous amount of connection possibilities there. That's going to have to connect ultimately with some interface circuitry, which is kind of my specialty. And that actually hooks up to the elevator we see here, but we're going to show you a lot of other things that you can do, all the bits and pieces that go into this. So as you may know already, Yo-Yo provides hardware interfacing that works on the open source Android libraries, and it's actually quite easy to program, and I think Wayne's going to talk a little bit about that now.
Okay. Oh, I think I have this on. Can you guys hear me? Oh, take it. Okay, I'm with it. All right. Yes, so the software, if you look at, did I hit the wrong button? I did hit the wrong button. Is it this next one? Okay.
Oh, actually, it's
yeah,
more hardware.
You want to talk more about that?
I'm not done yet. Okay, so we'll just give you a quick overview here. This is what the yo-yo board looks like. We didn't have a chance to rehearse, so forgive us. The yo-yo board is actually quite small. It costs about $50. You can get it online. It's got 48 general purpose I/O, digital I/O, analog I/O. It does counting, and it can actually do serial communications. We didn't get that far in this one today, but you can see up here there's the connections for the pins for power. On the lower part down here, you can see that if you're going to be using the Bluetooth dongle, which we're using today, you have to provide your own power supply, which is easy to come by, so you solder a couple of wires on here. It's got analog input that can handle a range from about 0 to 3.3 volts, so I'll talk a little bit more about that later on. And here are the actual pins that are available for analog I/O. There are 16 of them available. Not all of them are capable of doing that, but these ones are. And there are also some pins on the bottom and the bottom of the side here that are what are called 5-volt tolerant, so you can actually put a little more voltage in there without blowing up the board. We'll talk more about that later on. And if you forget about what those pins are, there's a little note right on the board. Now it's Wayne's turn.
All right. The software leverages several open source technologies, including Java, Eclipse development environment, and the Android development kit. And we combine them with the Yo-Yo development kit to produce hardware Android interface applications. When building an Android application, we want to be able to connect our Android application to the GUI components. So we do that when the Android activity is first created. Then we, so that's just an example there. Now where Yo-Yo fits into this is Yo-Yo, we're simply going to replace the Android activity with a special Yo-Yo activity that gives us connection to the Yo-Yo device. We end up creating a particular class called the Yo-Yo Looper class. And the Yo-Yo Looper class is going to be how we're going to connect our Yo-Yo device to our Android application. During a setup portion, we actually assign the hardware I/O pins. And then there's a loop, in a loop that runs continuously in a separate thread, our Android application will interact with our Yo-Yo hardware. We also need to override create Yo-Yo Looper method to be able to instantiate and create an instance of our Looper class. So I'm going to walk through that, those very simple steps in an example shortly. Because we're communicating over Bluetooth, we also have to make sure that our Android application has permission to use Bluetooth within our Android device. So we do that in the manifest of our Android application. We simply add that we are requesting Bluetooth permission. Now, a couple other considerations to consider. We want to be able to have updates come back to our Android device and be able to display. And because the Yo-Yo Looper runs continuously in a separate thread, we have to make sure that any updates that we're doing to our Android user interface are being done through the UI thread, not through the Looper thread. So we have to carry that information back to the GUI thread. Now, one other consideration to keep in mind, though, is that we don't want to inundate the UI thread with continuous updates. So we have to be careful about the frequency in which we send those updates. Otherwise, the Android device becomes non-responsive, and that's not what we want. OK, so I'm going to do a quick demo for you just to see how you can quickly put together a very simple application. This one will just simply turn a red LED on our test board here. And I'm just going to walk you through the steps very quickly. Oh, I'm up here, yeah. OK, so I guess I need to do this still. All right, so what we're going to do is start by just creating an Android project. Actually, I'm not sure. So I'll simply call it My Android Project, and we'll just take all the defaults. Now, because we want to just simply turn an LED on and off, we're going to just replace this label with a toggle button. We'll just leave the default name for it. And then in our Android code, we're simply going to connect to that. Okay, and we're just going to refer back to the toggle that we put onto the Android screen. There's our toggle button 1. Okay. Now, in order for us to be able to connect to the Yo-Yo libraries, we have to add that to our project. So we simply go into our project properties, and we click on Android. And if I scroll down, I see a spot where I can connect the Yo-Yo library. So there's just 2 libraries. These are just freely downloadable from the Yo-Yo, from the GitHub website. Links will be provided later for you guys so you can find all this. And now that we've been able to connect the Yo-Yo libraries, we simply replace our Android activity with a Yo-Yo activity. Now we just simply create our looper class. It just extends from the basic Yo-Yo looper. And we override those two methods that I mentioned, the setup and we override the loop. So now what we need to simply do is now connect to our hardware by indicating which pin. So I'm going to make a private static int called LED pin. And I know that it's configured on the hardware already on pin 48. So I'll say it equals to pin 48. And we create a digital output for that LED. So it's yo-yo.digital output, and we're going to be using the LED pin that we just configured. Open LED output. Oh, sorry, not here. Let's do that. Move that. We do that in the setup. Okay. And then lastly, in the loop, we now simply want to read the current value of the toggle button and be able to update or send that to the Yo-Yo device so that it mirrors what we have set on our toggle. So if the toggle is on, it turns the LED on, and off will turn the LED off. So we're simply going to say on the LED IO, we're going to write, and whatever the current value of the toggle button is, so I'm going to read the toggle button. So if it's checked, then the LED will be on. If it's not checked, the LED will be off. Okay, so we just need to now create an instance of our looper class by overriding the create Yo-Yo looper, and we simply return an instance of our looper. So return new looper. Okay, so that's it for the code. Very simple to put together. The only other thing we have to do is still get access to our Bluetooth. So we simply going to go to our manifest, and in our permissions, we simply want to add a user permission for Bluetooth. Find it. There it is. Okay. Now I'm going to just simply upload this to the tablet. The tablet's connected through USB. So I simply deploy it to the tablet. And I'm going to show you the tablet down here in just a second. Okay, can you see the tablet? No, not yet.
We can move this. Just to point out here, this is the actual Yo-Yo here. We've got a number of devices we're going to be interfacing today, but we have to kind of move over here. We'll zoom out.
I think we have to do a zoom out, yeah.
Yeah.
Oh, that's in. That's out as far as you go. Okay.
That's fine. You can work with that.
Can you see the LED?
Yes.
All right. Okay, so the Yo-Yo is on, and now let's see if we can see the yellow LED. Can you see the red come on? Did it come? Okay.
Yes.
So as I hit the button, you can see the red LED come on. You can see the red LED go off. Okay. So it didn't take very much to put that together. So all we do now is we take that and we can build a little more elaborate program on the user interface side and how we manage the hardware and what hardware we manage. So Chris is now going to come back and tell you a little bit more about the hardware interfacing side. So this one down here. Oh, sorry. Thank you.
Okay. So Wayne showed the software side of that. I just want to point out some general principles when interfacing with any microcontroller, including the yo-yo. At the output of every digital output is something we call a totem pole. We've got two different types of MOS, insulated gate MOS transistors, which might look a little bit intimidating, but when we realize what they're really doing, it's really quite simple in a way. The logic output is controlled by either connecting the output to basically the power supply or ground, which is typically 3.3 volts. So we can think about those two outputs as, or those two transistors as one being on or the other one being on. If the top one's closed, then the output is high. If the bottom one's closed, the output goes low. And in some outputs, there's something called a tri-state, where you can actually go into a third state. The output is floating. It's neither connected to the top or the bottom, which may be necessary if you're going to connect these things to multiple devices that are sharing, say, a bus or a line. So in the case of floating, we might want to make sure that a state is either high or low. We might want to provide some pull-up resistance or some pull-down resistance. Usually a 10 kilo ohm resistor is sufficient for that. If we're looking at outputs, sometimes we can actually connect those directly to the microcontroller, in this case the yo-yo. For instance, in Wayne's case, what we actually did was he just took the output of pin 45 or
48, yeah,
and connected it directly through a limiting resistor through an LED. As simple as that. When we do it in this case, the current's going to flow through there directly from the voltage which is going to be provided when it's triggered. That's called sourcing. So when we connect a load like the LED in this case, in this way, it's called low side sourcing because the LED is actually connected to the ground. Another alternative would be to connect the LED with a limiting resistor to the power supply. A current would flow, and now we say that the output is sinking current. We refer to that as high side because the load is on the high side. So we say that sometimes we can connect the load directly to the output here. The practical issues we have to be involved with is that the source, sink, and source current is limited. For instance, for the yo-yo board here, the output can only really source or sink about 20 milliamps, and we can only really work with a voltage of about 3.3 volts if we're sourcing and sinking about 5 volts. So we'll talk more about what we do if we want to do more than that in a moment. If I'm using a digital input, all of those pins, or many of those pins, can be configured to be inputs or outputs. We might want to put a momentary switch, we'll demonstrate in a moment, on one of those lines. You'll notice I've got a pull-up resistor there. So when that switch is normally open, it's not being pushed, the input to that, the input state would be a high. And when I push the button, it's going to short it to ground, and it's going to go low. So the logic state is high until the switch is pushed, in which case it'll be grounded. The other side is I can put the switch on the other side of that stack, and the input would be normally in a low position. When I push the push button, it would be connected directly to the voltage, so it would go high when pushed. Another possibility for an input we'll demonstrate as well is the optical slot sensor, which could be used for position detection, say in robotic applications, or in triggering an event. And we have a device like that here. They're about $1 at sale. You can probably get them a lot cheaper at DigiKey if you buy them in bulk. And basically you've got an LED on one side and a photo transistor on the other. And the light from the LED is turning the transistor on, and when it's blocked, something else happens. So that's how I connect up the LED. Just put a limiting resistor on to get that thing bright. I put a pull-up resistor on the other side and then go into the logic input. I have to make sure, though, that I pick a small enough resistor there that that LED is bright enough to turn the transistor on. These are just small matters. Notice how I'm not doing any ohms law calculations here. You can do a lot of work by just playing around. If you understand the basic principles, you're just picking up resistors and sticking them in and trying it. Think, well, maybe it's not turning on. I'll try a different size resistor. That's what you can do. You don't have to be intimidated by that. If I block the pathway between the LED and the photo transistor, for instance, I'm demonstrating here, the light is not going to turn on that transistor, and the output will go high. It'll be pulled up. If, on the other hand, I remove the blocking, the light will return to that, and that will pull the input down to ground again. So I've got a high and a low status. I can be checking for position of things. And this is often used by our students doing final projects in robotics realms and things like that. So Wayne's going to give us a little demonstration of that right now.
Okay, so we're connected to the yo-yo. I think we have to zoom in. Is that legible, sort of? Okay, so what we're going to show is a couple things that Chris had mentioned. So the LEDs, we had the two LEDs, the red LED, which you saw before, which is the pull, that's the source. Sourcing. The yellow LED, which is syncing. So you can see that one come on. We have the you have the switch that he mentioned. So you notice that when I turn the switch, it will switch from on to off to on as I push the push button switch, so we can get that feedback coming back. And also with the IR sensor, if I block it with this card, you can see it turn to on, and then to off, and then to on, and then to off. Okay, so now we're managing those inputs and outputs and communicating that back wirelessly through Bluetooth back to the Android software.
So that's all we'll say about the digital input and output for the moment. I want to talk a little bit about the analog capabilities. Analog is basically a voltage that could be changing over any value, not just one of two states. And it has a number of different capabilities here. For instance, if I had a 1.5 volt battery and connected it to what's called an analog to digital converter. Yes?
Sort of backing up slightly, what kind of delay are you looking at between, say, him inserting that card and going through Bluetooth and actually getting
what sort of latency?
Yeah.
We were noticing something on the order of maybe a half a second.
Yeah, yeah. It's not something that you're going to use for some kind of a real-time capture. So it's more, yeah.
We're still working on that. There's a number of interesting things we noticed about this. We really haven't pushed it to the limit yet, but we just started getting into this, and we noticed exactly that issue.
Part of the delay is depending on how you capture it. If you're doing polling, which is what's happening right now, you also you're taking a thread of the Android operating system. If that Android operating system becomes slowed down or bogged down with things, then that can increase your latency time.
So for an analog input, we use something called an analog to digital converter, which is built in here. Any DC or AC voltage can serve as that source. And basically it's sampling at a certain rate of speed and turning that into some sort of binary number. If I want to vary that, I can actually use a potentiometer, sometimes called a pot, and I can vary the what's called the wiper, or the middle pin of that, up and down to change the voltage. The yo-yo has 16 pins that can act as analog inputs, as I showed you earlier. The thing we have to be careful about is that the voltage range must not exceed the 0 to 3.3 volt range. If you do, you're probably going to damage the input. So what you have to do is scale the input by putting some kind of a potentiometer on there, or do some other kind of signal conditioning before you do that. So if you're going to hook up something with a potentiometer here, you put a supply voltage of 3.3 volts. And that's one of the pins that you have on the yo-yo board. You have 5 volts and 3.3 volts. So you can connect that to there with impunity. You won't damage the board. And we're going to demonstrate that now.
All right. So we're first going to demonstrate the potentiometer. So we're doing an analog input. And as you can see, as I increase you can see the bar increase. You might not be able to read the volt reading, but it's reading now, for example, 2 volts. If I go a little bit further, 2.6, 2.7, all the way up to 3.3 volts as I come down. So you can see the bar decreasing. Okay. The second thing we're going to demonstrate is the, sorry, not yet.
I would just say, too, that by itself maybe doesn't look very interesting, but there's a wide variety of things that you can do with this analog input. For temperature detection, the position of a motor or an arm on a robot, it just goes on and on. It's just a matter of making sure you scale it to the right voltage. You can even do a signal that's changing relatively rapidly. But there's this particular version of yo-yo. I think they're working on this. The maximum sampling rate is about 1 kilohertz or 1 kilosample per second. Yes?
The bar is moving around to sort of indicate, is that a limitation on the sampling accuracy or a limitation on the, I can't tell, is it the potentiometer you're using?
No, it's not the potentiometer. Just as we were setting this up here, the lead to my capacitor that would have swelled, quietened down the noise that I think is causing that broke, and I don't have a spare one. So that's an issue, right? But if you want to smooth that out, you have to put some kind of decoupling capacitor on there. We're also using switching power supplies here. There's probably a lot of noise.
You can't do that smoothing by software or anything?
Well,
You could.
yeah, you could. You could do some kind of an averaging or something like that to smooth it out. But we had originally had a capacitor on there, hardware, and then when that broke, we didn't have time, of course, to change the software. So.
But then the other thing is if you're averaging in software, that introduces another latency on top of the one built into the Android Bluetooth dongle. So you just have to say, okay, it's a trade-off at the moment. And at the moment, the sampling rate on this is not high enough to do audio applications. If it's sampling at 1 kilohertz, for instance, Nyquist says you can only go up to 500 hertz. But that's still enough for motor control applications, which we'll demonstrate in a moment.
Might be almost enough for telephones. I'm not quite sure what telephones are.
Telephones go up to about 3.4 kilohertz, so you have to sample usually about 8 kilohertz. I think the newest yo-yo is coming out, will improve matters greatly, but we're just working with the one we have at the moment. Come back to this, I think. Okay, we'll talk about analog output now, moving quickly. It also has a digital to analog conversion capability. For instance, if I take some sort of a binary number and I go through what's called a DAC, I'm going to come out with some kind of a voltage. That's the way a normal DAC would work. However, the DAC in this particular device, in a lot of microcontrollers these days, is increasingly going to something called pulse width modulation, or PWM. The value that we actually put into the DAC changes what's called the pulse width of a constant frequency signal, which we can set up in software. For instance, if I have a series of pulses here, that would represent one value. If I increase the value that I'm putting to the DAC, the pulse width would increase, and so further on like that. If I want to turn that into DC voltage, I could again use a capacitor, and what we would find is that the average level, if I take the area under the curve, would increase as the pulse width increased. So this can actually be used to control a great number of things like motors, as we'll demonstrate in a moment, or you could filter that and actually turn it back into an audio signal if your sampling rate was high enough. And this is called a Class D amplifier. And this is basically what a lot of your MPEG players and stuff are using these days, something very similar to this. So the average level rises as that happens, and we're going to do a bit of a demo for this now.
Yeah, not yet. All right. All right, so we have the motor here, and you can see as I increase the duty cycle, the motor speed will increase as I increase the duty cycle. So that's full speed there. If I come down about halfway, you can probably see it. Maybe not see it. Maybe you can hear it. Slowing down, almost stalling the motor at this point. Okay. Now what we can do is we can actually look at the duty cycle on a scope and be able to see as the pulse width is increase and decrease. So we're going to put that up on this scope and project it into the VGA. And we're going to be able to see the pulse width increases. And I'll put the microphone down so you can hear the motor increase and decrease at the same time. Okay. Okay. So that's the demonstration how you can hear the motor speed increasing and decreasing as the pulse width increases.
issue of isolation. It's fine when you're turning on LEDs and low voltage things, but we have to worry about isolation. Generally, when interfacing with the real world, we need what's called isolation. In other words, we want to have no electrical connection between this low voltage yo-yo board that's working on 3.3 volts and maybe 120 volts AC, or maybe a lot more. You don't know. You want to have that capability. So optical isolation links the controller, in this case the yo-yo, with a device driver using infrared. And there are many devices that do this. For instance, here's a variety of different ones. The 4N25, 26, 27 is a solid-state device that provides this isolation. If you want something bipolar, the H11AA2 is good. For telephones, for instance, when you want to detect if the phone is ringing, the voltage might go in both directions, so I've used this for that application. And Chris Tyler actually put me onto this LCB 710, which is an opto-MOS relay, which I've been finding incredibly useful. They're turning up everywhere now. So basically, we connect the I/O output or a sensor input to one of these sides and the device and the I/O on the other side. So it can go both ways so that our yo-yo is completely isolated from the high voltage application, because all you have to do is lift up a pin the wrong way and you could be in trouble. So it provides a barrier, and the only thing connecting those two parts of the circuit together is an infrared beam of light. And that just brings up the other idea of power driving. We're actually doing that for the motor here. There's a lot of optically isolated drivers available on the market to hook up with low voltage devices like the yo-yo. The opto-MOS relay is one of them. Here's an example of one. This actually handles about 9 amps. You can actually get a lot bigger one. It'll work with DC or AC. Here's an exact example of a solid state relay. We've got some other examples here. You can get examples of these that will work with AC or DC up to the hundreds of amps range. So go all the way from a couple of milliamps down to hundreds of amps. Okay, I'm actually going to, we've actually, actually going to demonstrate something here using 120 volt light.
Okay, so this is very similar to turning on the LED, the exact same application, just that it's now being driven through the device here. Oops. Okay, so we're able to turn on the light with the same ease as we were able to turn on an LED.
And what's nice about these type of devices is that you don't even have to provide a limiting resistor on here. You just have to hook up the output of your yo-yo or microcontroller directly to one of these things, and it does all the rest of the work for you. It's very, very handy. All right, so what we're going to do now is we're going to switch things over and actually do the star attraction here, which is the elevator that Andrew Ng and Rolando Singh interfaced. And just give us a moment for that.
No, you can put it up here. Okay, I'll just hold this here. No, it's not on yet. Yeah, there it goes.
So the elevator is now going into what's a home position. This is an example of using a whole bunch of different digital I/O and combining it together to do an actual practical application.
Is that readable? Okay, so make sure. Okay, so I'm just checking if it's readable. Okay, so now we can choose a floor, and so this is now an integrated application which is looking at several inputs, several outputs to be able to monitor where the elevator is, when the doors are open, when the doors are closed. We can pick a floor. It's going to go up to the second floor, open the door, close the door. Now, if Chris happens to, well, you're not fast enough there. I'll do it on the next floor. Okay.
Even sounds like my elevator.
Okay, if Chris happens to put his fingers in the door because he's running in late and he's trying to catch the elevator, it does react and make sure that it doesn't hurt him on the way in. Okay. If we hit several floors, it was smart enough to be able to determine which floor to stop at first and go in the same direction. If I hit another floor that's higher, it will finish going down in the direction it was going to the first floor, just as you would expect an elevator to do.
So it's important to remember that what's actually happening here is that the interface circuitry is exactly the sort of thing we've been talking about before, but it's actually connected to the the tablet wirelessly by a Bluetooth dongle. It's quite really amazing. Quite amazing.
Yeah.
All the decisions are being made, including sensing, the sensors and everything, are being made over on the laptop.
In the tablet.
Connected.
In the tablet, yeah.
On the tablet.
Yes, that's correct. And yeah.
So just in concluding, we've said that everything is really easy to do here, and that's a relative term. Wayne's pretty quick with his programming, but there are an enormous amount of resources available. We'll be providing a link to FSOSS, to this presentation and all these links here. You can learn how to do this yourself. It's not really that daunting a task, and it's a lot of fun. In summary then, we've shown that Android can allow programming of tablets and cell phones. It allows for easy interfacing with devices like the yo-yo for real-world devices. And if we simply adhere to simple principles that I've outlined here about interfacing, you can hook it up to a wide variety of devices and voltages, currents, and so forth. You're only limited by your imagination. And what we're finding in the school is that breaking down these kind of barriers for students, whether they're programming people or hardware people, really, really engages students a lot. They get really excited when they can start making something happen like this. So, Wayne, I just wanted to thank you very much for your attention and see if there's any questions you had.
Back.
As a novice in this area, and I'm certainly intrigued and inspired by these demos and these talks, I got a question, a general question. Google, in their ADPA, they recommend Arduino over certain other devices. Can you outline some of the key differences between the yo-yo device and Arduino, and if you recommend a beginner device?
I haven't actually had a chance to look at the Arduino yet, so I can't really comment on that. But what I have found with the yo-yo is extremely easy to use. With the yo-yo API, the yo-yo libraries, they do a lot of background code for you, so connecting through the Bluetooth to the device and then passing it on to you once that connection is made. But I can't comment on the Arduino, sorry.
I could say something about the Arduino. The Arduino is basically based on C programming, whereas the Android, it basically is Java programming. So it just depends on which environment you're more comfortable with, but they both have enormous amounts of libraries and online resources. And maybe the price is different. The Arduino is about $30, it's about $50. I think those are coming down.
Is there any provision in Android for real-time programming, or are there guarantees for latency or anything if you code a certain way?
Depending on, like, one of the things with the yo-yo that we hadn't looked at is that it can actually do captures, so buffering of signal transitions, and then you could take that in later on through the Bluetooth, so that you've eliminated the issue about the latency, because then you can actually see when the pulses came in or when the changes on the inputs came in. But because it's a multi-threaded operating system, that you do have to worry about what happens if your thread is busy, or the device is particularly busy. You have that issue of multi-threading. It's a Java operating system, so as far as priorities and things like that you can do for your threads, it's same as available because it is Java. Any other questions? Any other questions? All right.
Well,
Thank you very much for